one small patch of sky, no wider to us than a grain held at arm's length, contained thousands of galaxies, and when James Webb looked deeper, some of them seemed too bright, too massive, and too chemically advanced for the age they belonged to. A galaxy only 290 million years after the Big Bang already carried oxygen. Early black holes appeared before they seemed to have enough time to grow. Even the expansion of the universe still refuses to give one clean answer. If this calm journey speaks to your curiosity, a like, subscribe, or share helps Calm Space Science keep creating thoughtful science videos for quiet minds and late hours. Thank you for spending your time here. Leave a comment with the country or city you're watching from, what time it is there, and whether this is for sleep, study, or a peaceful pause. The story begins with Webb's golden mirror, unfolding far from Earth to receive the oldest light still arriving. On Christmas Day in 2021, the James Webb Space Telescope left Earth folded inside the nose of a rocket, carrying a design that had been shaped around one central problem. The oldest useful light in the universe no longer arrives in the form human eyes can see. It has been stretched by expanding space until it reaches us as infrared radiation, a kind of light associated with heat, dust, and deeply distant objects. Webb was built to receive that light with unusual care. Its purpose was not simply to take sharper pictures than earlier telescopes, and it was never only a larger version of Hubble. It was a different instrument for a different part of cosmic history, made to look past the limits that had held astronomy close to the younger, brighter, more easily visible universe. The first requirement was size. Hubble's primary mirror is a little over 2 meters across, already large enough to change modern astronomy, but Webb's mirror is much wider, about 6.5 meters across, built from 18 hexagonal pieces arranged into one reflecting surface. Each segment is coated with a very thin layer of gold, because gold reflects infrared light efficiently. The mirror is not large for beauty. It is large because the light Webb seeks is extremely faint. A galaxy near the beginning of cosmic history sends out light that has travelled for more than 13 billion years before reaching the telescope. During that journey, the signal weakens, spreads, and shifts. Only a large mirror can collect enough of it to make the object more than a trace in the data. Yet a mirror this large could not fit inside any available rocket as a single piece. It had to fold, along with its supporting structure and its instruments, and then unfold itself after launch. That made the telescope as much a mechanical achievement as an optical one. The mirror segments had to move into place with extraordinary precision. The sun shield, a 5-layer structure about the size of a tennis court, had to deploy in space after being packed tightly for launch. Its job was to keep sunlight, earthlight, and heat from the moon away from the cold side of the observatory. Without that shield, Webb would be blinded by its own warmth before it could measure the weak infrared glow of ancient galaxies. The reason is simple. Anything warm emits infrared light. A telescope designed to study faint infrared signals must be kept very cold, or its instruments will record the heat of the observatory itself instead of the universe beyond it. Webb therefore had to travel far from Earth to a stable observing region known as the second Lagrange point, where the gravity of the Sun and Earth allows the spacecraft to remain in a steady position with relatively little fuel. This location is nearly 1 million miles away. It is not close enough for astronauts to visit in the way they once visited Hubble. If a major part had failed during deployment, the mission would likely have ended before the science began. That fact gives the early phase of Webb's story a quiet technical weight. The telescope had hundreds of critical actions to perform after launch, and many of them had no simple backup if the hardware did not behave. The sun shield had to open, the layers had to separate, the secondary mirror had to swing into position, the primary mirror wings had to lock, the segments had to align. Each step narrowed the difference between a folded machine and a working observatory. When the deployment succeeded, the task was still not finished. The mirror segments had to be adjusted until they acted like one smooth surface. Even though they were separate physical pieces, their positions were corrected by tiny amounts until the reflected light came together properly. Only after this alignment could Webb focus with the clarity required for its science. Its instruments also had to cool deeply, because infrared astronomy depends on cold conditions as much as it depends on large mirrors. In this sense, Webb's first achievement was not a discovery in the sky. It was the creation of the observing conditions that made such discoveries possible. The telescope had to become quiet enough, cold enough, and accurate enough to receive signals that had been travelling since the universe was young. The need for infrared vision comes from the expansion of space itself. Light travels as waves, and as the universe expands, the space carrying those waves expands as well. A wave that began as visible or ultraviolet light can be stretched until it becomes infrared by the time it arrives here. Astronomers call this redshift, because stretching light moves it toward redder wavelengths and eventually beyond visible red into infrared. The farther away a galaxy is, the longer its light has usually been travelling, and the more the universe has expanded during that travel. Looking far across space therefore becomes a way of looking back in time. This is not because telescopes change time, but because light has a travel time. When Webb observes a galaxy whose light has taken billions of years to arrive, it records that galaxy as it was when the light began its journey, not as it may be now. For the earliest galaxies, this makes infrared detection essential. Their light is not simply dim, it has been moved into the range Webb was built to study. Hubble could see farther than any previous optical telescope in many cases, and its deep fields revealed thousands of galaxies in regions of sky that looked empty from the ground. But Hubble was not designed mainly for the coldest infrared wavelengths that carry much of the signal from the earliest galaxies. It could reach some of that territory, but not with Webb's sensitivity, mirror size, or instrument design. This difference matters because the early universe is not only distant, it also passed through a major transition before the cosmos became as transparent as it is now. After the first atoms formed, space was filled with neutral hydrogen gas. For a long period, this gas made the young universe difficult for light to cross freely. Then the first stars and galaxies began to form. Their radiation changed the gas around them, stripping electrons from hydrogen atoms and gradually clearing the fog. Astronomers call this period the epoch of reionization. It marks the time when the universe moved from a mostly opaque state into one where light from galaxies could travel across enormous distances. Webb was built to study this transition by detecting the redshifted light of objects that existed during and before much of that clearing process. This is one reason its discoveries can feel so disruptive. It is looking not merely at old galaxies, but at a time when the basic conditions for observation were still being established. The telescope is also able to separate light into spectra, spreading it into wavelengths so that astronomers can identify chemical fingerprints and measure redshift more securely. A picture can show shape and brightness, but a spectrum can show whether a distant red object is truly from the early universe, or only appears red for another reason, such as dust. This distinction is important because early claims about very distant galaxies often begin as candidates. They require confirmation. Webb's instruments were designed to provide that confirmation more often and more accurately than earlier observatories could. Infrared spectra can reveal hydrogen, oxygen, carbon, and other elements, along with clues about temperature, star formation, dust, and active black holes. The telescope is therefore not only collecting ancient light, it is sorting that light into evidence. The scale of the instrument can be misunderstood if it is described only through its cost, engineering difficulty, or famous images. Its deeper role is to move astronomy into a region of evidence that had been partly inaccessible. Webb does not make the universe larger. It makes more of the already existing universe measurable. It does not remove uncertainty. In many cases, it sharpens uncertainty by turning vague possibilities into specific tensions. Before Webb, models of the earliest galaxies depended on the best available data, along with simulations of dark matter, gas cooling, star formation, and feedback from young stars. These models were not careless. They were built over decades and tested against many observations, but they were also built with limited access to the first few 100 million years of cosmic structure. Webb entered that gap. Its large mirror, cold instruments, infrared sensitivity, distant orbit, and spectroscopic power all serve the same scientific purpose: to compare what theory expected with what ancient light actually shows. That comparison is where the importance of Webb begins. The telescope's first months did not simply produce impressive images. They opened a more direct route into a period when galaxies were assembling, the cosmic fog was lifting, and the first heavy elements were beginning to appear from Earth. This period had always been partly hidden by distance, by redshift, by the atmosphere, and by the warmth of instruments not cold enough to listen cleanly. Webb was designed to remove those barriers one by one. By the time its mirror was aligned and its instruments were ready, the observatory had become a quiet receiver stationed far from Earth, shielded from heat, waiting for infrared light that had started its journey before the Milky Way had anything like its present form. The first question was whether it would work as planned. The answer came quickly. The harder question was what the universe would look like once this older light could finally be measured with enough detail to matter. That answer was not as simple, and it began with a tiny patch of sky filled with more galaxies than ordinary intuition can easily hold. On July 11th, 2022, Webb's first deep image reached the public as a quiet test of scale. The target was a galaxy cluster known as SMACS 0723, sitting billions of light-years away, massive enough for its gravity to bend the paths of light passing near it. The cluster itself was important, but not because it was the oldest object in the frame. Its value came from what it did to the light behind it. Like all large concentrations of mass, it curved space around itself, and that curvature acted as a natural lens. Galaxies located far beyond the cluster, too faint for ordinary detection, had some of their light magnified and distorted as it travelled through the cluster's gravitational field. This effect, called gravitational lensing, had been used before, but Webb made it unusually productive. In a patch of sky small enough to seem empty without a powerful telescope, the image contained thousands of galaxies. Some appeared as clear points and small oval forms. Others were stretched into arcs by the lensing cluster. Many were red, not because they were simply red in the ordinary visual sense, but because their light had travelled for so long through expanding space that it had been shifted into infrared wavelengths. The image became famous partly because it was beautiful, but its scientific importance was more specific. It showed that Webb could turn a tiny area of sky into a layered record of cosmic time, where nearer galaxies, more distant galaxies, and deeply magnified background systems appeared together in one field. The size of the field matters. The portion of sky shown was often compared to a grain held at arm's length. But the useful point is not the comparison itself. The useful point is that a very small direction in space can contain an enormous number of galaxies when a telescope is sensitive enough to separate them. Each galaxy in the image represents not only many stars, but a system with its own history of gas, dust, star formation, mergers, and chemical change. The frame, therefore, did not simply display a crowded sky. It compressed many stages of cosmic history into one observation. For astronomers, this was not a symbolic moment. It was a practical one. Webb had demonstrated that its mirror, cooling system, instruments, and infrared detectors were working together at the level needed to study the early universe. Hubble had already observed deep fields and had shown that apparently empty regions of sky are full of galaxies. Webb did not replace that achievement. It extended it into wavelengths and distances where Hubble's view became more limited. One of the clearest differences came from exposure time and detail. Hubble had spent long periods collecting light from some of the deepest fields ever made. Webb could reach comparable or greater depth more quickly, and in infrared it could bring out structure that had once appeared only as faint smudges. The difference was not only that the new telescope saw more objects, it saw more physical information. In some galaxies, the brighter central region could be distinguished from surrounding material. In others, shape and colour, variation hinted at different stellar populations or dust content, where older images had left distant galaxies as uncertain traces. Webb could often begin to show whether they were compact, extended, dusty, actively forming stars, or distorted by intervening gravity. This was the first sign that the telescope would not merely add distant points to a catalogue. It would make early galaxies into objects that could be studied with more internal detail. The image also carried an immediate caution. The most distant and faintest features were not all simple to interpret. A red galaxy in a deep field can be truly ancient, but it can also appear red because dust absorbs bluer light, or because its stars are old and cool, or because lensing changes how its light is gathered. The first image, therefore, did not settle the history of the first galaxies by itself. It opened a field of candidates, clues, and uncertainties. That caution is important because Webb's early discoveries soon became part of a wider public story about galaxies that appeared too large, too bright, or too mature for their age. The first deep field was not yet a crisis. It was a warning that the region Webb was entering contained objects that would require careful confirmation. Astronomers could see faint red systems whose distances and properties needed spectra, not just colours. A spectrum separates light into wavelengths, making it possible to measure redshift more directly and identify chemical features. Without that step, a distant-looking object can be misunderstood. With that step, it becomes a firmer piece of cosmic history. In the first deep image, the gravitational lens added both power and difficulty. It magnified background galaxies, allowing Webb to detect objects that would otherwise be too faint. But lensing also distorts shape and brightness. To understand a lensed galaxy, researchers must model the mass of the foreground cluster and estimate how much the background light has been magnified. A galaxy may look brighter because it truly is producing a great deal of light, or because the lens has amplified it. It may appear stretched because of gravity, not because the galaxy itself has that form. This means that the image was both revealing and demanding. It gave astronomers access to hidden objects, while also requiring careful reconstruction before those objects could be weighed, dated, or compared to theory. Webb's strength was that it could begin that process with better data than previous instruments had provided. The background galaxies were not just marks in a distant field, they were possible tests of how quickly matter gathered after the Big Bang, how efficiently gas cooled into stars, and how early heavy elements began to appear. In standard galaxy formation, structure grows from small beginnings. Dark matter gathers first, forming invisible halos. Gas falls into those halos, cools, and forms stars. Young stars then change their surroundings through radiation, winds, and supernova explosions. This process is not expected to be perfectly slow everywhere, but it does have limits. Gas cannot turn into stars with perfect efficiency. Radiation from young stars can push material away, Supernovae can heat and stir gas that might otherwise collapse. The earliest galaxies should therefore be small, faint, and still assembling, with only a minority growing quickly under favourable conditions. The first deep field did not overthrow this picture, but it showed why Webb might test it more severely than expected. If objects at very high redshift were already bright and structured, then either star formation began earlier or proceeded more efficiently in some places, or the objects had been misread in the first analysis. Those possibilities are very different, and Webb was built to separate them. The image also changed the emotional scale of the question in a restrained but real way. The universe had already been known to be large, and Hubble had already taught that deep space is filled with galaxies. Webb's first image added a different kind of pressure. It showed that even a minute field could contain enough information to challenge the timing of cosmic development. A small patch did not feel small once its contents were understood as a sequence of distances, ages, and histories. The cluster in the foreground was billions of years old in the light-reaching Webb. The background galaxies were older in the sense that their light had departed earlier in cosmic history. Some of the reddest points might belong to periods when the universe was still young enough for the first major structures to be forming. All of this appeared together because light from different depths arrives at the telescope at the same time. The image was therefore not a flat picture of one moment. It was a set of overlapping look-back times, gathered through one line of sight. That is why the first deep field mattered beyond its visual impact. It provided an early demonstration of Webb's ability to turn distance into sequence and infrared light into evidence. It also showed that the next phase would have to be more rigorous. Images could reveal candidates, but spectra would decide which candidates truly belonged near the beginning of cosmic history. Brightness could suggest mass, but measurements would have to determine whether that light came from stars, dust, or active black holes. Shapes could suggest mature structure, but lensing and resolution would have to be accounted for. The warning in the image was not that astronomy had been wrong in a simple way. It was that a better instrument had reached a region where several assumptions could finally be tested at once. The first deep field was therefore a threshold observation. It confirmed that Webb could see deeply, but more importantly, it showed that deep seeing would not automatically produce simple answers. The ancient universe was now less hidden, and because of that, it was about to become more difficult to explain. The dedicated deep surveys began where the first image could not go far enough. A single field had shown that Webb could detect faint red galaxies and use foreground gravity to reach deeper than ordinary viewing allowed. But the oldest parts of cosmic history require more than a striking frame. They require repeated observations, carefully chosen patches of sky, and enough spectral information to separate genuine early galaxies from objects that only appear ancient. This was the purpose of programs such as the James Webb Advanced Deep Extragalactic Survey, often called JADES, which returned Webb to regions already studied for years by Hubble. Those older observations mattered because they gave astronomers a baseline. Hubble had mapped the visible and near-infrared sky as deeply as it could, building catalogues of faint galaxies and identifying candidates from the first billion years. Webb entered those same fields with stronger infrared sensitivity, a larger mirror, and instruments able to gather spectra from extremely faint targets. The goal was not simply to find more distant objects. It was to measure them well enough that their place in cosmic history could be tested. In early galaxy work, that distinction is essential. A colour-based estimate can suggest that a galaxy is far away, but a spectrum can confirm the distance by identifying how much known features in the light have been shifted by cosmic expansion. Once that redshift is measured securely, the galaxy becomes a time marker. Its light left when the universe was at a particular stage, and its brightness, size, and chemical features can then be compared with models of how structure should have grown by that time. When the first spectroscopic results from these surveys appeared, they confirmed galaxies from only a few 100 million years after the Big Bang. Some were seen as they existed roughly 300 to 450 million years after the beginning of cosmic expansion. At the time, these were among the most distant galaxies directly measured. Their existence alone didn't break cosmology, because models already allowed the first galaxies to form early. The tension came from how visible some of them were. They were not all weak traces sitting near the edge of detection. Several were bright enough to suggest strong star formation, and some appeared more developed than the simplest expectations had allowed. That mattered because the standard picture of cosmic growth is gradual. In the lambda cold dark matter model, dark matter begins as a framework of invisible gravitational wells. Gas falls into those wells, cools, and forms the first stars. Small systems merge into larger ones. Radiation from young stars pushes back against infalling gas. Exploding stars heat their surroundings and scatter heavy elements. The process can be uneven, and rare objects can grow quickly. But the early universe is not expected to build many bright galaxies immediately. It has limits on available time, available gas, cooling speed, and star formation efficiency. Webb's surveys began to show that the earliest visible population might be richer than those limits had suggested. This did not mean the model was useless. It meant the region where the model had been least tested was now becoming visible, and the first comparison was uncomfortable. The pressure increased as candidate lists grew. Surveys across different fields began finding more bright galaxies from the first several 100 million years than many simulations had predicted. Some studies reported that luminous early galaxies appeared much more often than expected. That result had to be handled carefully, because candidate galaxies can be misleading. Dusty galaxies at later times can mimic some colours of very distant systems. Active black holes can add light that is not starlight, making a galaxy appear more massive or more rapidly star-forming than it truly is. Gravitational lensing can magnify a source and complicate its intrinsic brightness. Even with Webb, the earliest universe is studied through weak signals, and weak signals demand caution. Yet caution did not erase the pattern. As spectra replaced estimates for more objects, it became harder to treat every surprising galaxy as a mistake. The surveys were not finding one impossible object in isolation. They were building a population. That population suggested that star formation may have begun earlier, proceeded more efficiently, or occurred in more concentrated bursts than many models had assumed. Each option changes the meaning of the early universe in a different way. Earlier star formation pushes the first luminous objects closer to the cosmic dawn. Greater efficiency suggests gas could collapse into stars under conditions that current simulations may not fully capture. More intense bursts imply that early galaxies may have been unstable. Compact systems capable of producing large amounts of light for short periods. None of these possibilities requires abandoning established physics, but each forces the details to be reconsidered. The important shift was from asking whether Webb could see the first galaxies to asking why it seemed to be seeing so many that were bright. That is a more precise and more difficult problem. A faint galaxy at great distance confirms that structure existed early. A bright galaxy at the same distance asks how rapidly matter became organized into stars. A group of such galaxies asks whether the early universe was generally more productive than expected. The surveys also widen the question of chemical development. The earlier stars should have formed from almost pure hydrogen and helium, because heavier elements were produced later inside stars and spread by stellar death. If a young galaxy shows signs of dust or heavier elements, then previous stars must already have lived and enriched the gas. That does not automatically mean the galaxy is mature in the modern sense, but it does mean the timeline contains earlier steps that are not directly seen in that object. Webb's spectra therefore do more than confirm distance. They can reveal whether a galaxy is chemically young or whether it has already been altered by earlier generations of stars. This turns every confirmed distant galaxy into a layered record. Its light gives an age. Its brightness suggests current or recent star formation. Its chemical features hint at an older history that must have happened before the observed moment. The deeper the surveys look, the more compressed those stages become. The universe was only a small fraction of its present age, yet some systems already appear to carry evidence of formation, growth, radiation, and enrichment. The difficulty for theory is not any single step. Stars can form early. Massive stars can live briefly. Galaxies can brighten in intense episodes. The difficulty is arranging enough of these steps in the available time without violating what is known about gas, gravity, radiation, and feedback. Webb also changed how astronomers think about selection. Before its launch, the earliest galaxies accessible to observation were expected to represent only the brighter edge of a mostly hidden population. Webb has indeed found faint systems, but it has also shown that the bright edge may be brighter and more populated than expected. This matters because the bright galaxies are the ones most capable of affecting their surroundings. Their young stars produce radiation that can ionize hydrogen and help clear the early cosmic fog. If there were more of them, or if they formed stars more intensely, they may have played a larger role in ionization than earlier estimates allowed. The history of visibility itself could be adjusted by Webb's results. A universe that made luminous galaxies sooner would also become transparent differently, because those galaxies would have altered the gas around them. In that sense, the surveys are not just counting objects, they are testing the relationship between early structure and the changing state of space. The emerging picture remains incomplete, but it is no longer empty enough for older assumptions to sit comfortably. The first billion years now contain confirmed galaxies, strong candidates, unexpected brightness, possible rapid enrichment, and a growing need to revise the small-scale details of formation. The standard cosmological framework still explains the broad shape of the universe well, including the growth of structure from early density variations and the large-scale distribution of matter. The strain appears inside the timing and efficiency of the first luminous systems. Webb has not shown that the whole foundation is wrong. It has shown that the early chapters may have been written with too much empty space between the first possible stars and the first clearly developed galaxies. The surveys into first light therefore change the question, from whether galaxies formed early to how much work they had already done before they became visible to us. That is where the next pressure point appears, because some early candidates seemed not merely bright, but massive enough to force the models into their most uncomfortable calculation. The galaxies later nicknamed universe breakers did not begin as a settled discovery. They began as an uncomfortable calculation. Webb had found very red sources in the early universe that appeared bright enough to contain enormous amounts of starlight at a time when the universe should still have been building its first substantial systems. In February 2023, a team studying Webb data reported 6 candidate galaxies that seem to exist within the first several 100 million years of cosmic history, some possibly between 500 and 700 million years after the Big Bang. Their estimated stellar masses were startling. Depending on the object and the assumptions used, they appeared to contain tens of billions, and in some cases perhaps around 100 billion, times the mass of the Sun in stars. Those numbers placed them near the scale of large modern galaxies, even though they were being observed when the universe was only a small fraction of its present age. The difficulty was not that massive galaxies can never form. The difficulty was that forming them so early required a sequence of events to run at extreme speed. Gas had to fall into dark matter halos, cool, collapse, and form stars with unusually high efficiency. The newly formed stars then had to produce enough light for Webb to detect them across more than 13 billion years of expansion. In ordinary models, that chain is limited by time and by feedback. Star formation is not a perfectly smooth conversion of gas into light. Young stars heat their surroundings. Massive stars explode. Radiation and winds can push gas away from dense regions. These effects reduce the speed at which a galaxy can keep making stars. A very early galaxy with a modest mass is not a problem. A very early population with masses comparable to later large galaxies is a different kind of claim. Because it asks the universe to assemble mature amounts of stellar material before many simulations allow enough time for the necessary steps. This is why the phrase universe break has spread so quickly, even though the science itself was more careful than the nickname. The issue was not that the entire standard model had already failed, it was that the most extreme interpretation of the data pressed against the allowed supply of matter. In some cases, the estimated stellar mass approached the total amount of ordinary matter that should be available inside the dark matter halo expected for that early period. If those estimates were correct, the galaxies would have converted nearly all accessible gas into stars with little waste and little delay. That level of efficiency is hard to reconcile with known star formation, especially under the turbulent conditions expected in young systems. The models could make rare bright galaxies, but they struggled to make several of them so soon. So massive, and so common in a small survey volume. Yet this was also the point where caution became essential. Stellar mass is not measured directly by simply looking at a galaxy. It is inferred from light. Astronomers compare the observed brightness and colour with models of stellar populations, dust, age, and redshift. A galaxy full of young, massive stars produces light differently from one dominated by older stars. Dust can hide some wavelengths and make a galaxy appear redder. An active black hole can add light from hot material falling inward, creating brightness that does not come from ordinary stars at all. When a source is extremely distant and faint, different combinations of these factors can fit the same limited data. A red object may therefore look like a massive galaxy, even if part of its light has another origin. Webb made the candidates visible, but visibility was only the first stage. The next stage was to test whether the redshifts were correct and whether the light was truly dominated by stars. Follow-up studies brought the first corrections. Some candidates that initially looked like very distant massive galaxies turned out to have more complicated explanations. A few may have been less distant than first estimated. Others remained distant, but had evidence that an active galactic nucleus, a feeding central black hole, contributed to the observed light. If a black hole is adding infrared emission, the galaxy's stellar mass can be overestimated. This does not make the original observations careless. It shows how difficult early galaxy interpretation becomes when multiple physical sources are blended into a tiny signal. As more data arrived, the most extreme claims softened. The largest mass estimates came down. The idea that several fully mature Milky Way scale galaxies existed almost immediately after the Big Bang became less secure in that sense. The crisis shrank. But the important part is that it did not disappear. Even after revised redshifts, improved modelling, and corrections for black hole light, Webb continued to find early galaxies that were too bright or too numerous, compared with many pre-launch expectations. The problem changed shape. It was no longer only about a few spectacular candidates. It became a broader question about whether the first galaxies formed stars more efficiently than expected, whether early stellar populations were brighter for their mass, or whether dark matter halos grew in ways that simulations had not fully captured at small scales. Each solution would leave the basic cosmological framework mostly intact, while changing the details of early galaxy formation. One possibility is that the first generations of stars differed from later stars. If early gas contained very few heavy elements, it may have cooled and fragmented differently, producing more massive stars on average. Massive stars are very bright for their mass and live short lives, so a young galaxy filled with them could appear more luminous without containing as much total stellar material as first inferred. Another possibility is that early galaxies formed stars in brief, intense bursts. A galaxy caught during such a burst would look unusually bright, but that brightness might not represent long-term steady growth. A third possibility is that feedback was less effective at stopping star formation in some compact early systems, allowing gas to collapse rapidly before radiation and supernovae disrupted it. None of these ideas is exotic by itself. The challenge is finding the right combination that can produce the observed population without creating conflicts with other evidence, such as the chemical state of the gas, the number of faint galaxies, and the timing of reionization. The Universe Breaker episode is therefore a useful example of how Webb changes science. It does not simply produce a surprising image and replace an old model overnight. It reveals objects that force several assumptions to be tested together: distance estimates, stellar population models, dust, black holes, lensing, star formation efficiency, and dark matter growth all become part of the same problem. A correction in one part can reduce the tension, while another observation can raise it again. The result is not a clean overthrow, but a narrower and more demanding uncertainty. Before Webb, many early galaxies were too faint to examine in this way. After Webb, their light is detailed enough to expose where the models are flexible and where they are strained. That distinction matters because the strongest scientific progress often comes from tensions that survive after the obvious errors are removed. The most inflated masses were not the final answer, but the remaining excess of bright early galaxies still carries meaning. It suggests that the first few 100 million years may have been more productive than the simplest versions of the timeline implied. Structure may not have waited politely for the pace imagined by older data. Gas may have reached high densities sooner. Stars may have formed in more concentrated episodes. Black holes may have added light to systems that looked at first like pure stellar populations. The early universe may have been less mature than the first headlines suggested, but it was also less empty and less slow than many models had expected. This is the quieter lesson of the Universe Breakers. The most dramatic interpretation weakened under scrutiny, as strong science requires, but the remaining evidence still points toward an early universe working near the edge of what current models can comfortably reproduce. The next problem is even harder to soften, because it does not depend only on how much starlight a galaxy appears to contain. It depends on chemistry. And chemistry keeps a record of stars that must have lived before the galaxy was observed. Jade's GSZ 14-0 entered the Webb record not because it looked complete, but because it appeared where very little time had passed. Its light began travelling when the universe was only about 290 million years old, an age so early that most of cosmic history still lay ahead of it. At that stage, space had not yet settled into the familiar pattern of mature galaxies and long intervals between them. The first stars were expected to be active, but the sequence of formation, death, enrichment, and renewed star birth was still thought to be limited by a narrow clock. Webb's confirmation of this galaxy placed a real object inside that clock. It was not just a red source whose distance had been guessed from colour. Spectroscopic evidence tied it to an extreme redshift, making it one of the most distant galaxies directly measured. That alone would have made it important, because each confirmed galaxy at such an early time becomes a boundary marker for what structure had already assembled. But the galaxy was also brighter and more extended than a minimal first galaxy might be expected to appear. It stretched across more than 1,000 light-years and carried the light of a substantial young system. The first question was how it had grown visible so soon. The deeper question arrived when later observations identified oxygen in its light, because oxygen cannot belong to the original material of the universe. The Big Bang produced mostly hydrogen and helium, with only small traces of a few light elements. Oxygen is made later, inside stars, through nuclear fusion, and it is released into space when massive stars shed material or die violently. Its presence in a galaxy so early means the galaxy was not made only from untouched primordial gas. Some stars must already have formed before the observed moment. Those stars must have lived their short lives, produced heavier elements, and returned them to surrounding gas. Then the enriched gas had to be present in the galaxy when Webb and follow-up instruments detected the signal. This is why the discovery is more demanding than a distance record. A distant galaxy says that matter had gathered. Oxygen says that matter had already gone through at least one cycle of stellar processing. Massive stars live briefly compared with stars like the Sun. Some can burn through their fuel in only a few million years because their cores are hot, dense, and under extreme pressure. In principle, an early generation of massive stars could form, enrich its environment, and die quickly enough to leave oxygen behind within the first few 100 million years. The problem is not whether the basic physics allows fast stellar death. It does. The problem is fitting that death into a larger sequence that includes the birth of the first stars, the gathering of gas into a galaxy, the mixing of heavy elements through that gas, and the rise of the stars whose combined light Webb observes. Gas must collapse under gravity. Cooling must allow dense regions to fragment. The first stars must ignite. Their radiation and explosions must alter nearby material. Enriched gas must either remain available or fall back into new star-forming regions. The galaxy then has to shine brightly enough for detection across the entire observable distance. Jade's GS-Z14-0 makes that sequence look compressed. It does not prove that the models are wrong in a single dramatic stroke, but it asks them to operate with less unused time than expected. The oxygen signal also changes how the galaxy is understood. Without it, the object could be described mainly through size, brightness, and redshift. With it, the galaxy becomes evidence of earlier unseen history. The stars that made the oxygen are not directly observed as individual objects. They are inferred from what they left behind. This gives the galaxy a hidden past inside an already ancient observation. Webb sees it as it was 290 million years after the Big Bang, but the chemistry points backward from that moment to events that had already occurred. That backward pressure is what makes early chemical enrichment so important. It turns a young galaxy into proof that something older than the galaxy's observed light must have happened first. The first stars, often called population 3 stars, are expected to have formed from nearly pristine hydrogen and helium. They have not yet been directly observed. Their masses, lifetimes, and effects on their surroundings remain uncertain. Many models suggest they may have been unusually massive, because gas without heavy elements cools differently from enriched gas. If they were massive, they would have lived briefly and produced strong radiation, possibly ending in powerful explosions. Such stars could enrich their surroundings quickly. But quick is not the same as effortless. Their remnants had to contribute to the gas from which later stars formed, and the chemical traces had to become widespread enough to appear in the integrated light of a galaxy. The oxygen detection therefore touches one of the main unknowns in early cosmology, how rapidly the universe moved from its first untouched gas to the chemically complex environments that later galaxies require. It is tempting to treat oxygen as a sign of maturity, but that would be too simple. JD's GS-Z14-0 was not mature in the sense of a present-day spiral galaxy with long-lived stellar populations, a settled disk, and many cycles of star formation. It was young, active, and probably very different from galaxies nearby. The oxygen means it was not chemically pristine. It had already been altered. That distinction is important because it avoids exaggeration while preserving the force of the evidence. The galaxy does not need to be fully developed to challenge expectations. It only needs to show that enrichment had begun earlier or moved faster than many timelines had allowed. Its importance is based on the connection between a faint spectral feature and the life histories of stars that are no longer present in the data as stars. A chemical line becomes a clock, not a perfect clock, because many physical paths can create similar levels of enrichment, but a clock that prevents the earliest universe from being treated as uneventful. The models now have to allow not only for early galaxy assembly, but also for the prior formation and death of stars capable of producing oxygen. There are possible ways to ease the tension. Star formation may have begun in dense pockets earlier than the average picture suggested. The first stars may have been massive enough to enrich gas rapidly. Early galaxies may have been compact, allowing heavy elements to mix through star-forming regions more quickly. The oxygen may also trace only part of the galaxy, meaning a localized enriched region could dominate the signal. Each explanation helps, but each has its own cost. Earlier star formation shifts the first luminous activity closer to the beginning of structure formation. Rapid mixing requires conditions that simulations must reproduce. A localized signal still requires prior enrichment in the right place at the right time. The discovery therefore does not offer a single contradiction. It offers a set of constraints that reduce the available freedom. What makes this especially significant is the way it connects to the broader Webb pattern. The telescope had already found candidates for bright early galaxies. It had already forced revisions to some mass estimates, while leaving a real excess of early luminous systems. Jade's GSZ 14-0 adds a different kind of evidence. Brightness can be partly explained by black hole light, by unusual stellar populations, or by short starbursts. Stellar mass estimates can be revised as models improve. Oxygen is not immune to uncertainty, but it carries a clearer physical meaning. It requires stars to have made it. That requirement places an earlier generation behind the observed galaxy, even if the number of generations and details of their deaths remain unsettled. The early universe is therefore not only building structures sooner, it is chemically transforming sooner. That transformation matters because heavy elements change everything that follows. They allow gas to cool in new ways, they contribute to dust, they influence the masses of later stars, they create the material basis for planets, and, much later, for chemistry far more complex than simple hydrogen and helium. In the first few 100 million years, oxygen does not imply anything like a habitable environment. It means the universe had already started the process of becoming chemically layered. From that point on, every new generation formed in a universe less pristine than before. Jade's GSZ 14-0 stands near the visible edge of that transition. It shows a galaxy young enough to belong close to cosmic dawn, yet enriched enough to contain the products of stellar death. The result is not a loud overthrow of cosmology, but a precise discomfort. The time between first collapse and first enrichment may be shorter than expected. The first stars may have acted more quickly, or more intensely, or in environments more favourable to rapid recycling than models had assumed. Whatever the solution, the galaxy makes the early universe harder to describe as a slow prelude. It had already begun turning simple matter into heavier elements, and that means the story of structure was also a story of chemistry from the very beginning. Once that is accepted, the next question moves inward. From the stars that enriched young galaxies to the dark engines that may have been growing at their centres just as early and just as unexpectedly. The black hole problem begins with a limit rather than an image. A black hole can pull gas inward, but it cannot always feed as quickly as gravity alone would suggest. As gas falls toward it, The material heats, brightens, and releases radiation. That radiation pushes outward on nearby gas. If the inflow becomes too intense, the light produced by the feeding process can begin to drive the fuel away, slowing the growth that created the brightness. Astronomers describe this balance with the Eddington limit, a practical ceiling on sustained black hole feeding under ordinary conditions. The limit does not make rapid growth impossible, but it makes it difficult to grow a small stellar remnant into a massive galactic centre in a short time. This is why Webb's early black holes have become such a persistent problem. The first black holes expected in ordinary models form after massive stars collapse. They may begin with only a few times, or perhaps a few tens of times, the mass of the Sun. To become the kind of black holes found at the centres of galaxies, they must feed, merge, or both. Given enough time, that path works. The Milky Way's central black hole is quiet now, but it still carries millions of solar masses. More active galaxies contain black holes with greater masses, surrounded by bright disks of gas. Nearby, such objects are impressive but not impossible. They have had time. Webb's difficulty is that it keeps finding evidence for large feeding black holes when time was still scarce. A black hole only a few 100 million years after the Big Bang cannot be treated as a late result of long growth. If it is already millions of solar masses, then either it began unusually large, grew unusually fast, or followed a channel not yet captured well by the simplest models. Each option changes the early universe in a different way. A large starting seed requires special formation conditions. Faster growth requires a way around the normal feedback from radiation. Repeated mergers require dense environments where black holes find one another efficiently. None of these routes can be dismissed, but none is easy to make common enough to explain the full population now coming into view. Webb's observations of early active galaxies sharpen this issue because they do not only reveal distant starlight, they also identify signatures of gas falling into central black holes. In some galaxies, the light is too compact, too energetic, or too broad in its spectral features to come from stars alone. A feeding black hole can produce strong radiation from a region much smaller than the galaxy around it. The material near the black hole moves at high speed, and this motion can widen the emission lines seen in a spectrum. When such features appear in very early galaxies, they imply that central black holes were already present and growing while their host systems were still young. One confirmed object from the first few 100 million years contains a black hole of around 1 million solar masses, actively taking in material at a rate that is difficult to maintain over long periods without unusual conditions. Other early systems point to black holes tens of millions of solar masses or more. The exact masses are still uncertain, because measuring a black hole at such distance depends on models of gas motion, luminosity, and orientation. Yet even cautious estimates are large enough to matter. The problem is not only the mass, it is the combination of mass, age, and frequency. A single early black hole could be a rare success, formed in an exceptional region with unusually dense gas and favourable growth. A growing set of early active black holes suggests that the mechanism may have been more common. This turns an isolated surprise into a formation problem. In the standard picture, the first stars appear, some die, black hole seeds form, and those seeds grow along with young galaxies. Webb's results compress that sequence. The seeds seem to become important quickly, sometimes before the surrounding galaxy has accumulated the kind of stellar mass seen in later systems. This reverses a familiar assumption. In many nearby galaxies, the mass of the central black hole and the mass of the surrounding stellar bulge follow a rough relationship. The galaxy and black hole appear to have developed together, each influencing the other through gas flows, star formation, radiation, and feedback. In some early Webb systems, that balance looks uneven. The black hole may be a large fraction of the host's mass, or its light may dominate the observed signal. This raises a basic question about order. Did galaxies build black holes, or did early black holes help shape the first galaxies around them? The answer may not be the same in all places. Some galaxies may have grown their black holes gradually from stellar remnants. Others may have formed heavier seeds when large gas clouds collapsed directly. Direct collapse is one of the main proposed solutions. Under very specific early conditions, a cloud of primordial gas might avoid fragmenting into many ordinary stars. If it remained hot and massive enough, it could collapse into a black hole seed far heavier than any single stellar remnant. Such a seed would begin with thousands or even tens of thousands of solar masses, giving it a strong advantage. It would not need to climb from the small mass of a dead star. It would already be partway toward the scale Webb observes. The difficulty is that direct collapse needs a narrow environment. The gas must lose support against gravity without breaking into smaller star-forming clumps. Radiation from nearby young galaxies may help by suppressing certain cooling pathways, but the conditions must be arranged carefully. Direct collapse can explain some early heavy seeds, but making it common enough remains challenging. Another possibility is that black holes sometimes grew above the Eddington limit. This can happen in theory if gas falls inward in a dense, thick flow that traps some radiation or channels it away. In such episodes, the black hole can gain mass faster than the usual steady limit would allow. Simulations show that short periods of this kind may be possible, especially in chaotic early galaxies rich in gas. The difficulty is duration. Webb's black holes often seem to require not only brief rapid feeding, but repeated or sustained growth over large fractions of the available time. A black hole feeding too aggressively should also disturb its surroundings. Its radiation can heat gas, launch winds, and reduce star formation nearby. Yet many early systems show both active black holes and strong star formation. That coexistence is not impossible, but it must be explained. It suggests that gas supply, geometry, and feedback may have behaved differently in compact early galaxies than in better studied systems later on. A third possibility reaches even farther back, before the first stars. Primordial black holes are hypothetical objects that could have formed from density variations in the very early universe. If they existed, some black holes would not need stars as their origin. They could begin before any galaxy existed, then act as heavy seeds once ordinary matter gathered around them. This idea is attractive because it solves the time problem directly. A black hole that starts large before star formation has a much easier path to becoming massive early. The cost is that primordial black holes have not been confirmed observationally. Their possible abundance is constrained by several kinds of evidence, and no current data requires them. They remain a serious but uncertain option, useful because Webb has made the ordinary routes look incomplete, but not yet proven by the telescope's discoveries. The early black hole problem therefore sits between known physics and missing history. Gravity, gas, radiation, and stellar collapse are familiar processes, but their combination in the first galaxies may have produced outcomes that were underestimated. Black holes may have formed from heavier seeds. They may have fed through dense streams. They may have merged in crowded young environments. They may have hidden inside galaxies whose light is difficult to separate into stars and accretion. Webb does not yet tell which path dominates, and it may reveal that several paths operated together. What it does show is that central engines appeared early enough to influence the galaxies around them, while those galaxies were still assembling. This changes the role of black holes in the story of cosmic dawn. They are not only late consequences of galaxy growth. In some cases, they may be active participants from near the beginning, heating gas, shaping spectra, adding light, and complicating estimates of stellar mass. The same discoveries that made early galaxies look unexpectedly bright may partly involve black holes hidden within them. The two problems are connected. A galaxy that appears too massive may be partly illuminated by an active nucleus. A black hole that appears too large may have grown inside the same dense conditions that made early star formation intense. The telescope is therefore revealing a young universe where stars and black holes cannot be separated cleanly. They developed in the same compact environments, drew from the same gas supply, and affected the same surrounding matter. The discomfort comes from timing. The engines are present before the ordinary schedule seems ready for them. The next step is to examine the compact red objects where this imbalance becomes most visible, because in those systems the black hole does not merely sit inside the galaxy. It appears almost large enough to redefine what the galaxy is. Little red dots were not named because they were simple. In Webb images they appeared as compact reddish points, small enough to look almost star-like at first glance, but their spectra showed that they were not ordinary stars in the foreground. They were distant systems from the early universe, many seen within roughly the first billion years after the Big Bang, and their light carried signs of both active black holes and young stellar populations. The name is informal, but the problem they represent is serious. These objects seem to gather several early universe puzzles into one small source. They are red, but not all in the same way. Some redness comes from distance, because cosmic expansion stretches their light into longer wavelengths. Some may come from dust, which absorbs shorter wavelengths and changes the colours that reach Webb. Some may come from hot gas close to a central black hole, wherein falling material produces strong radiation. Separating those contributions is difficult because the sources are so far away and so compact. A large nearby galaxy can be divided into visible regions, with a centre, a disk, and separate knots of star formation. A little red dot often arrives as one blended signal. Webb can spread that signal into a spectrum, but the spectrum still has to be interpreted through models. The first interpretation was striking. Many little red dots seem to contain black holes with masses between millions and tens of millions of solar masses, and in some cases perhaps more. That alone would have been notable at such early times. The deeper issue was the ratio between the black hole and the surrounding galaxy. In the present universe, central black holes usually make up only a very small fraction of the stellar mass of their host galaxies, often around 0.1%. The exact relationship varies, but the general pattern is clear enough that astronomers use it as evidence of shared growth between galaxies and their central black holes. In many little red dots, the black hole appeared to account for a far larger share of the system. Some estimates placed it at a few percent or far higher. An early report suggested cases where the central black hole seemed almost too large for the host around it. The galaxy looked less like a mature system containing a central engine and more like a compact environment in which the engine was already one of the dominant facts. This is not a small adjustment to scale. It changes the order of the story. If black holes normally grow alongside galaxies over long periods, then a young galaxy with an already oversized black hole asks how that central mass got its head start. One explanation is that the black holes began from heavy seeds in the direct collapse pathway. A large cloud of primordial gas avoids fragmenting into ordinary stars and falls inward almost as a single object, creating a black hole much larger than a remnant from a single dead star. Such a seed would be able to reach millions of solar masses much sooner. This idea is physically plausible under restricted conditions, but the restrictions matter. The gas has to stay hot enough, dense enough, and coherent enough to collapse without breaking apart. Nearby radiation may suppress cooling and help the process, but too much disturbance can also disrupt the cloud. Direct collapse can help explain the existence of early heavy black holes. It is harder to use it to explain a large population, unless the early universe produced those special conditions more often than current models suggest. A second explanation is rapid feeding above the usual Eddington limit. This does not require a very large initial seed. Instead, it asks the black hole to gain mass quickly through dense inflows of gas. Early galaxies were rich in gas and more compact than many later systems, so the environment may have allowed feeding episodes that would be less common today. In some models, radiation escapes more easily along certain directions while gas continues falling inward from others, allowing growth to exceed the standard limit for a time. The difficulty again is not the existence of the process. It is the amount of growth required and the length of time over which it must continue. If little red dots are common, then rapid feeding cannot be a rare accident. It must be a recurring part of early black hole growth. That creates a second difficulty, because a strongly feeding black hole does not remain passive. Its radiation can heat the surrounding gas, drive winds, and interrupt star formation. Yet the spectra of many little red dots also show evidence for young stars. The central black hole and the surrounding stellar population seem to be active together. A model must therefore explain how gas can keep reaching the black hole while also continuing to form stars nearby, without one process quickly shutting down the other. A third explanation reaches back before stars and galaxies. Primordial black holes, if they exist, would have formed from dense regions in the very early universe, not from stellar collapse. They could provide large seeds without needing the first stars to form and die first. This possibility would solve the timing problem in a direct way, because some black holes would begin early enough and massive enough to grow into the objects Webb observes. But primordial black holes remain hypothetical. They have not been confirmed, and their possible abundance is limited by observations of gravity, background radiation, and the distribution of matter. They are attractive as a solution because they give black holes more time. They are difficult as an explanation because they introduce a population that has not yet been independently established. The little red dots therefore sit in a narrow space between ordinary mechanisms that may not be sufficient and extraordinary mechanisms that remain unproven. Later studies added another layer of caution. Some of the light first attributed to feeding black holes may come from stars after all, especially young, hot stars producing strong ultraviolet radiation. If that is true, the black holes in some little red dots may be less dominant than the earliest estimates implied. This correction would reduce the tension, but not remove it. Even with more starlight included, the objects remain unusual. They are compact, numerous, distant, and spectrally different from most galaxies nearby. Their existence suggests that the early universe contained a population in which black hole growth, star formation, dust production, and chemical enrichment were closely mixed inside small systems. That mixture makes them hard to classify using categories shaped by the modern universe. Nearby galaxies provide many examples of active galactic nuclei, starbursts, dusty galaxies, and compact systems. But the little red dots combine these features at an age when the surrounding cosmic environment was very different. Gas supplies were higher, heavy elements were fewer but increasing, galaxies were smaller and more disturbed. Radiation from early stars and black holes was helping change the state of intergalactic hydrogen. The same physical processes existed, but they acted in conditions that have no exact local match. Webb's task is to collect enough spectra to separate these possibilities. The width of emission lines can reveal fast-moving gas near a black hole. The shape of the continuum can suggest dust or stellar populations. Chemical features can show how enriched the gas has become. X-ray observations from other telescopes can help identify active black holes, though many early objects are too faint for easy confirmation outside infrared wavelengths. Each new observation reduces the freedom of interpretation, but it also shows why a single answer may not cover the whole class. Some little red dots may be black hole dominated, Others may be compact star-forming galaxies with dust. Some may contain both, with the balance changing from object to object. The category may not be one kind of object at all, but a temporary observational grouping for several early pathways that look similar in Webb's filters. This possibility is scientifically important because it warns against treating the red points as a single mystery with one solution. The early universe may have produced a range of compact systems whose differences are only beginning to separate as data improves. What remains constant is the pressure they place on timing. Whether the light comes mostly from black holes, young stars, or both, these objects require rapid assembly. They require gas to gather, collapse, heat, enrich, and radiate in a short interval. They require central masses to grow or shine early. They suggest that the first billion years were not only a period of faint beginnings, but a time when small systems could become extremely intense. This does not make the modern universe less real or less orderly. It suggests that the calm relationships measured in nearby galaxies may be the later outcome of a more uneven early phase. Over billions of years, mergers, feedback, gas loss, and continued star formation may have brought galaxies and black holes into the rough balances observed today. Little red dots may preserve an earlier stage before that balance was established. They are not final answers. They are compact records of an unsettled period, where the growth of black holes and the growth of galaxies were still negotiating their relationship. Once that is recognized, the scale of the question widens again. These small red objects are not isolated curiosities. They formed inside a larger arrangement of matter, filaments, clusters, and empty regions whose structure was also beginning to take shape earlier than expected. The cosmic web is not visible in the same direct way as a galaxy. A galaxy can appear as a concentrated source of light, with stars, gas, dust, and sometimes a bright central region. The web is larger and more indirect. It is the pattern formed when galaxies and clusters are placed on the biggest scales, not evenly scattered, but arranged along long filaments and gathered into dense knots with large underdense regions between them. This structure is not a decorative feature added late to the universe. It is the large-scale result of gravity acting on small differences that were already present in the earliest measurable state of matter. After the Big Bang, the universe was extremely uniform, but not perfectly uniform. Tiny density variations gave gravity the first unevenness to work with. Regions with slightly more matter pulled in more material. Regions with slightly less matter gradually became emptier. Over time, this produced a connected arrangement of filaments, clusters, sheets, and voids. Ordinary matter, the material that later formed stars and planets, followed the deeper gravitational pattern shaped mostly by dark matter. Dark matter does not shine, absorb light in ordinary ways, or reveal itself through spectra like gas does. Its presence is inferred from gravity from how galaxies move, how light bends near massive structures, and how the overall distribution of matter must behave to match observations. In that sense, galaxies are the visible traces of a much larger mass arrangement that remains mostly unseen. Webb's importance is that it can begin to extend the study of this arrangement toward earlier times. It does not map all dark matter directly, but it observes faint galaxies that mark where matter had already collected. When those galaxies appear in groups, chains, or developing clusters at high redshift, they show that the large-scale structure was beginning to organize while the universe was still young. This matters because the same timing problem found in early galaxies and black holes also appears in cosmic architecture. The standard model expects structure to grow from small beginnings, with dark matter halos merging, gas collecting, and galaxies forming inside the deepest gravitational wells. On very large scales, the model has been successful. It explains why the universe has a web-like distribution rather than a smooth spread of galaxies. It also explains why clusters sit where filaments intersect, and why large empty regions open between denser zones. The tension appears when particular structures seem more developed, more massive, or more coherent at earlier times than simulations had commonly predicted. Webb's deep surveys have revealed not only isolated early galaxies, but galaxies that appear to occupy shared environments. Some are candidates for early protoclusters, loose ancestors of the galaxy clusters seen later in cosmic history. A protocluster is not yet a settled cluster with galaxies moving inside a deep, fully mature gravitational well. It is a region where many young galaxies have formed close enough together that gravity may eventually bind them into a larger system. Finding such regions early means that matter had already gathered into significant overdensities. This does not violate the basic idea of gravitational growth, but it can sharpen questions about how quickly the first dense environments assembled. If galaxies were forming efficiently in these regions, then the densest parts of the web may have become active earlier than the average universe. That distinction is important. The universe does not evolve at the same pace everywhere. Dense regions move ahead, empty regions fall behind. A telescope that can detect faint early galaxies is especially likely to find the accelerated history of the densest environments, because those regions produce more light. The question is whether the observed abundance and brightness of those early structures fits comfortably within that expected variation. In some cases, it does. In others, it presses close to the limits. The cosmic web also changes how individual discoveries are interpreted. A very bright early galaxy may seem less surprising if it sits in an unusually dense region, where gas supply is larger and mergers happen more often. A rapidly growing black hole may be easier to understand if it forms at the center of a strong matter concentration, where inflows are frequent and the surrounding galaxy is compact. Early chemical enrichment may proceed faster if many massive stars form near one another and return heavy elements into a shared environment. In this way, the web provides the setting for the smaller puzzles. It does not remove them, but it offers a reason they may cluster in particular places. The earliest unusual objects may not be typical of the whole universe. They may be the bright tips of the densest regions, the places where gravity had the strongest early advantage. Even so, those places still have to exist in the right numbers. A model cannot explain every surprise by placing it in a rare, dense environment if such environments become too common in the data. The balance between rarity and abundance is one of the central tests. Webb adds to that test by observing small fields deeply and wider fields, with enough sensitivity to identify patterns in galaxy distribution. The more area it covers, the better astronomers can distinguish a rare, overdense patch from a wider population. The deeper it observes, the more it can detect the faint galaxies that surround the bright ones. That surrounding population matters. A single luminous galaxy may be an exceptional object. A luminous galaxy embedded in a crowd of fainter companions points to a larger environment. A cluster of such systems becomes evidence that the web had already developed recognizable features. The result is a shift from studying early galaxies as separate islands of light to studying them as members of a growing structure. This approach also makes dark matter more central to the story. Stars are the visible result, but dark matter sets much of the underlying arrangement. In the standard model, cold dark matter moves slowly compared with the speed of light in the early universe, allowing it to clump on small scales and form the halos where galaxies grow. If early galaxies appear too abundant, one question is whether star formation inside halos is more efficient than expected. Another is whether the halos themselves are more numerous or more massive than expected. Webb cannot answer that alone, because it sees light rather than dark matter. but by measuring how many galaxies exist at each brightness and distance. It helps infer how many halos must be present, and how efficiently those halos turn gas into stars. Large-scale structure therefore becomes a bridge between visible astronomy and invisible mass. Each early galaxy is not only a source of light, it is also a marker of a dark matter environment. When many such markers appear together, they trace the growth of the web. The scale involved is difficult to reduce to ordinary terms without losing precision. Filaments can extend across hundreds of millions of light years. Galaxy clusters can contain hundreds or thousands of galaxies bound within a shared gravitational region. Voids can be larger still, not empty in an absolute sense, but containing far fewer galaxies than average. Across these scales, the universe is neither uniform like a smooth gas nor chaotic like a random scatter. It has a statistical structure. Cosmology tries to explain that structure using the same initial conditions that also explain the cosmic microwave background. The oldest light that can be observed directly. The strength of the standard model comes from how much it connects. It links early density variations, dark matter growth, galaxy clustering, and the large-scale pattern seen today. Webb's early findings matter because they test whether the first luminous objects fit naturally into that connected picture. So far, the answer is mixed. The broad framework remains strong, but the first bright galaxies, early black holes, and possible dense environments suggest that the detailed formation of visible structure may have been faster or more uneven than expected. This is not a failure of scale. It is a demand for better detail. The architecture of the cosmic web also prepares the next question, because a web contains not only dense filaments and knots, but also large underdense regions. Those voids affect what galaxies form, how matter flows, and how observers inside them measure the universe. If the Milky Way sits in an unusual part of the web, then the local view may carry a bias of its own. The bigger structures are therefore not only distant arrangements to be mapped, they may influence the numbers used to describe cosmic expansion itself. Webb's early galaxies show how fast the universe built light. The cosmic web shows where that building happened. The next problem begins when the place of observation becomes part of the measurement, and the large-scale structure around the Milky Way stops being background and becomes evidence. A void is not truly empty, but it is empty enough to change the meaning of structure. In the cosmic web, matter gathers along filaments and into clusters, while other regions lose material over time and become underdense. These underdense regions can contain galaxies, gas, dark matter, and faint light, but far less of them than the cosmic average. Their importance is not only that they are large, it is that they show how uneven the universe becomes when gravity has billions of years to amplify small early differences. Dense regions grow denser as matter falls inward. Sparse regions become more sparse as matter flows away toward the surrounding filaments and walls. The result is a universe where location matters. A galaxy does not sit in a neutral background. It sits inside a gravitational landscape, shaped by nearby clusters, empty regions, and the slow motion of matter across enormous distances. The Bhuta's void is one of the clearest examples of how large these underdense spaces can be. Discovered in the late 20th century, it spans roughly 330 million light-years and contains far fewer galaxies than a region of that size would normally be expected to hold. It is not a perfect cavity. It is not a place where matter is absent, but compared with the average cosmic density, it is unusually sparse. The discovery was striking because it forced astronomers to take seriously the scale of emptiness inside the cosmic web. Clusters and filaments are easier to notice because they contain light. Voids are harder because they are defined by what is missing. Yet that absence is a physical condition. It affects how galaxies are distributed, how matter moves, and how the large-scale universe is modelled. A void also changes the observational situation of anything inside it. If a civilization existed near the centre of a very large void, the nearest bright galaxies beyond its own might be much farther away than they are for the Milky Way. The history of astronomy from such a location could develop differently, not because the laws of physics change, but because the available evidence would be arranged differently in the sky. This is a quiet but important point. Observation is always made from somewhere. The universe may be governed by the same laws in every direction, but the local arrangement of matter can influence what appears nearby, what is easy to measure, and what has to be inferred with difficulty. The Milky Way is not thought to sit in a void as extreme as Boötes, but there is evidence that it may lie within a large underdense region known as the KBC void. This proposed structure is much broader and gentler, possibly extending across roughly 2 billion light-years. It would not look like a dark hole in the sky. It would be a statistical underdensity, a region with less matter than the average when measured across very large scales. The idea remains debated because identifying such a broad structure depends on galaxy surveys, distance measurements, selection effects, and assumptions about how completely the nearby universe has been mapped. Still, the possibility matters because a local underdensity could affect measurements that use nearby galaxies. In a void, matter tends to move outward toward denser boundaries. Galaxies inside or near the edges can acquire motions that are not only due to the general expansion of the universe, but also to the gravitational pull of surrounding denser regions. These additional motions are called peculiar velocities, meaning velocities caused by local gravity rather than by cosmic expansion alone. If those motions are not modelled correctly, they can slightly alter the inferred expansion rate. This connection does not automatically solve any major cosmological problem, but it makes the observer's address scientifically relevant. The Milky Way also belongs to a much larger flow of matter called Laniakea, a supercluster identified by mapping galaxy motions rather than only galaxy positions. Laniakea spans roughly 500 million light-years and contains more than 100,000 galaxies. Its boundaries were drawn by following how galaxies move through the gravitational field around them, revealing a vast region whose matter is streaming towards shared attractors. The Milky Way sits inside this flow, not at a privileged centre, but as one small galaxy participating in a much larger motion. Within Laniakea, galaxies are drawn toward a dense region known as the Great Attractor, and beyond that, toward even larger concentrations such as the Shapley concentration. These names can make the structure sound more settled than it is. A supercluster is not bound in the same simple way as a small galaxy group. Cosmic expansion is still active across these scales, and some parts may never collapse into one object. What matters is the flow pattern. Galaxies move through a landscape shaped by uneven mass, and that movement records where matter has accumulated. This is why the local universe is more than scenery around the Milky Way. It is part of the measurement system through which cosmic expansion, galaxy motion, and large-scale structure are interpreted. Webb's discoveries of early galaxies do not directly map the KBC void or Laniakea, but they belong to the same broader issue. The telescope shows that the early universe may have formed luminous objects faster or more efficiently than expected. Large-scale surveys show that matter today is arranged in filaments, clusters, and voids, with flows that depend on the uneven distribution of mass. Between these two views lies the history of structure growth. Early density variations became dark matter halos. Halos gathered gas. Gas formed stars and galaxies. Dense regions became active first, while underdense regions emptied out. If the first galaxies were brighter or more numerous than models predicted, then the growth of structure in the earliest dense regions may need revision. If the local universe is underdense, then the measurement of expansion from nearby galaxies may need careful correction. These are separate questions, but they share one principle: the universe cannot be understood only by averaging it. The average density matters, but the departures from that average are where galaxies form, black holes grow, voids open, and observers make measurements. This does not mean that cosmology is helplessly local or biased beyond repair. Modern cosmology is built precisely to handle such effects, using large surveys, statistical methods, background radiation, supernova, gravitational lensing, and many independent checks. The concern is more subtle as measurements become more precise. Effects that once seemed small can become important. A local underdensity that would have been negligible in a rough measurement may matter when the disagreement between methods is only a few units in the expansion rate. A peculiar velocity that once looked like noise may matter when many galaxies are used to calibrate distance. A survey selection effect may matter when scientists are trying to decide whether a void is real, how large it is, and whether it is deep enough to influence local observations. The more precise the instruments become, the more carefully the surrounding structure must be understood. Webb sharpened the distant side of this problem by improving the view of early galaxies. Other surveys sharpen the nearby side by mapping where galaxies are and how they move. Together they show that scale alone is not the main difficulty. The difficulty is connecting conditions across scale from the first small density variations to the first bright galaxies. To present day filaments and voids, to the local motion of the Milky Way within a larger flow, the idea of cosmic address therefore carries a scientific meaning. It does not make Earth central, it does the opposite. It places the Milky Way inside a particular environment whose properties must be measured rather than assumed. The galaxy is part of a local group, inside a supercluster flow, possibly within a broad underdense region, surrounded by structures that pull and shape motion across hundreds of millions of light years. From such a position, astronomers measure redshifts, distances, velocities, and brightness, then use them to infer the behavior of the universe as a whole. Most of the time, that process works because the methods are designed to average over local irregularities. But when attention remains after years of checking, local structure becomes one possible place to look. It may not provide the full answer. It may provide only a correction. Or it may show that the disagreement comes from somewhere deeper. What the voids make clear is that empty space is not irrelevant space. It participates in the cosmic web by marking where matter is not, by guiding flows toward where matter is, and by reminding cosmology that observation always begins from a physical location. The next question follows naturally from that reminder. If the local environment can influence how nearby galaxies appear to move, then one of the most basic numbers in cosmology, the rate at which the universe expands, must be examined with unusual care. The expansion problem begins with a number that should describe the whole universe, yet depends on how the measurement is made. That number is often called the Hubble constant, although it is not a simple constant in the everyday sense. It expresses how fast space is expanding now, by relating the distance of a galaxy to the speed at which that galaxy appears to recede as space stretches between it and us. A more distant galaxy, on average, recedes faster. This relation is one of the foundations of modern cosmology. It helps set the scale of cosmic distance, the age inferred for the universe, and the timeline used to interpret every galaxy Webb observes near the edge of visible history. For many years, the expectation was that better measurements would make the value converge. Instead, two of the best methods have continued to return different answers. One method begins with the early universe. It uses the cosmic microwave background, the faint afterglow from the time when the universe first became transparent to light. That radiation preserves tiny temperature variations from very early cosmic history. When those patterns are analysed within the standard cosmological model, they imply a present expansion rate of about 67 kilometers per second per megaparsec. A megaparsec is a large distance unit, equal to a little more than 3 million light-years. The second method begins much closer to home and builds outward through distance measurements. It starts with objects whose distances can be measured directly, then uses stars with known brightness behaviour to calibrate distances to nearby galaxies, and then uses especially bright stellar explosions to reach farther into the universe. This method often gives a value closer to 73 kilometers per second per megaparsec. The difference may look small when written as ordinary numbers, but the precision of both methods makes it difficult to ignore. The error ranges do not overlap easily. The gap has reached a level that, in physics, usually means the disagreement is unlikely to be a random accident. This is the Hubble tension. It is not a disagreement between careless measurements. It is a disagreement between carefully checked paths through cosmic evidence. The early universe method looks backward to the oldest light and calculates forward. The local distance ladder looks outward from nearby objects and builds upward step by step. If the standard model is complete and all measurements are free of hidden bias, the two routes should meet at the same value. They do not. For a long time, one of the most reasonable hopes was that the local distance ladder contained a subtle observational error. The ladder depends on crowded fields of stars in other galaxies, especially variable stars whose changing brightness reveals their true luminosity. If those stars are blended with nearby stars in older images, their brightness can be misread. A small error at one rung of the ladder can spread upward, because each stage calibrates the next. Hubble had performed much of the work that made the local value precise, but Hubble's images, especially in crowded regions, could still leave room for concern. Webb was expected to test that concern. Its infrared vision and sharper resolution allowed it to observe many of the same distance markers with less confusion from dust and less blending from nearby stars. If the local value had been inflated by crowding or instrumental limits, Webb should have moved it closer to the early universe value. That did not happen. Webb's measurements supported the earlier local result rather than removing it. This was an important outcome because it reduced one of the most comfortable explanations. Better resolution did not make the tension fade. A new instrument, designed very differently and operating in infrared from a stable point far beyond Earth, found that the local ladder was not obviously wrong in the way many had hoped. This does not prove that no systematic error remains anywhere. It means the easiest instrumental explanation became much harder to defend. Other teams have used different distance indicators, including the brightness limit reached by certain older red giant stars, and some of those studies find values closer to the early universe estimate. That keeps the debate open. The field has not settled on a single interpretation. What makes the problem serious is that each side has independent reasons for confidence. The cosmic microwave background is measured with great precision and fits the standard model very well across many features. The local distance ladder has been refined for decades and has survived many checks. Webb strengthened part of that local chain instead of weakening it. The result is a tension that now sits less like a loose measurement and more like a question about whether something in the model, the methods, or the local environment has been missed. The local environment returns here with real importance. If the Milky Way lies within a broad underdense region, then nearby galaxies may have motions influenced by the pull of denser matter around that region. These motions can add to or subtract from the clean expansion signal that cosmologists are trying to measure. A galaxy's redshift includes the expansion of space, but it can also include motion caused by local gravity. When distances are nearby enough for those motions to matter, a large underdensity could slightly alter the measured expansion rate. In this view, the local ladder might not be wrong because of bad instruments. It might be measuring the universe from inside a region that is not perfectly average. That idea is attractive because it uses known physics. Voids exist. Galaxies flow toward denser structures. Local gravity affects motion. The unresolved question is size and depth. The proposed underdensity would need to be strong enough and modelled accurately enough to explain the difference. Some analyses suggest it can reduce the tension but not erase it. Others argue that its effect may have been underestimated. The possibility remains contested, but it illustrates why cosmic address matters. A precise measurement from inside an uneven universe may need correction before it can be treated as global. There are also more fundamental possibilities. The early universe calculation depends on the Standard Model, including assumptions about dark matter, dark energy, ordinary matter, radiation, and the geometry of space. If something behaved differently in the early universe, the value inferred from the cosmic microwave background could shift. Perhaps there was an additional form of energy before the first atoms became visible. Perhaps neutrinos or other light particles affected the expansion in a way not fully accounted for. Perhaps dark energy itself is not as simple as the Standard Model assumes. These ideas are not accepted solutions. They are examples of the kind of changes that theorists consider when measurements refuse to agree. The difficulty is that the Standard Model fits many other observations. Any new ingredient must fix the expansion problem without damaging the parts that already work. That is a high standard. Webb's role in this crisis is specific. It did not create the Hubble tension, and it does not solve it by itself. It checked one of the most important local measurements with a stronger tool and found that the discrepancy remained. This result matters because it changes the nature of uncertainty. Before Webb, it was easier to imagine that the problem would fade with cleaner images. After Webb, the problem looked more durable. It may still be a hidden systematic error, but not the simple one that Webb was especially well placed to find. It may be a local structure effect, but that effect has to be large enough and consistent with surveys. It may be new physics, but new physics must satisfy a wide range of evidence beyond one number. The expansion rate is therefore not an isolated parameter sitting at the edge of cosmology. It runs beneath the whole interpretation of Webb's distant universe, the age assigned to a redshift, the distance inferred for a galaxy, the growth time available for an early black hole, and the meaning of a galaxy seen a few 100 million years after the Big Bang all depend on the cosmological model used to translate light into history. The current tension does not make Webb's discoveries meaningless. It makes their context more delicate. A galaxy still has a measured spectrum. A redshift still tells how much its light has been stretched. But the broader timeline into which that galaxy is placed is tied to the same framework that contains the unresolved expansion problem. This is why the Hubble tension carries more weight than its modest numerical difference suggests. It is a disagreement about scale, age, and the reliability of cosmic inference across time. The universe is not offering two visibly different appearances. It is offering two precise routes to one value, and those routes do not yet meet. Webb has made the ancient universe clearer, while leaving this underlying mismatch intact. The next uncertainty reaches deeper still, because the expansion rate describes how fast space is stretching now, while dark energy asks what is driving that stretching, and whether the force behind it has truly remained unchanged. Dark energy is not observed as a substance in the ordinary sense. It is inferred from what the universe does at the larger scale, where galaxies are not merely moving through space, but space itself is expanding between them. Since the late 1990s, the evidence has shown that this expansion is accelerating. Something acts like a pressure built into the universe, causing distant galaxies to recede faster over time than gravity alone would allow. The name dark energy is a placeholder for that unknown cause, It describes the effect more clearly than the thing itself. In the standard model of cosmology, dark energy is usually treated as a cosmological constant, meaning its density stays the same as the universe expands. Matter becomes thinner as space grows, because the same amount of matter occupies a larger volume. Radiation also thins and loses energy as its wavelengths stretch. A true cosmological constant behaves differently. Its energy density remains fixed in empty space. So as more space appears, the total influence of dark energy grows relative to matter. This simple assumption has been powerful because it fits many observations well. It helps explain the present acceleration, the large-scale structure of the universe, and the patterns measured in the cosmic microwave background. It is also mathematically clean. The difficulty is that clean does not always mean complete. Recent surveys of large-scale structure have begun to test whether dark energy has truly behaved like a constant across cosmic history, and the first signs are no longer perfectly comfortable. One major approach uses the distribution of galaxies as a record of expansion. In the early universe, sound waves moved through the hot plasma of matter and radiation before atoms formed. Those waves left a preferred scale in the later distribution of galaxies, a subtle pattern known as baryon acoustic oscillations. The name is technical, but the idea is straightforward. The pattern acts as a kind of standard ruler. By measuring how that ruler appears at different distances and times, astronomers can reconstruct how the expansion of the universe has changed. A new generation of surveys has measured millions of galaxy redshifts to build a three-dimensional map of cosmic structure with exceptional reach. When these measurements are combined with other evidence, including the cosmic microwave background and supernova distances, the results have suggested that dark energy may not fit the simplest constant model as neatly as expected. The statistical evidence is not yet at the level where physics would treat it as a settled discovery. It is strong enough, however, to matter. Some analyses have found that dark energy may have weakened over relatively recent cosmic history, rather than remaining perfectly fixed. That is a careful statement, because the result depends on combining data sets and testing models with assumptions built into them. It does not prove that the cosmological constant is wrong. It shows that the best current measurements are beginning to leave room for a more complex behavior. This matters because dark energy controls the future of expansion. A small change in its behavior can become a large change in the fate of the universe. If dark energy is constant, the universe continues accelerating in a stable way. If it weakens, gravity may matter more in the distant future than the standard picture suggests. If it strengthens, expansion could eventually become far more extreme. The question is not only what dark energy is doing now, but whether its past behavior gives away its long-term direction. Physicists describe dark energy partly through a value that relates its pressure to its energy density. For a cosmological constant, this value has a fixed form. If observation suggests that the value differs from that fixed form or changes over time, then dark energy may be something more like a field. A field can evolve, it can roll slowly, store energy differently, and change its influence as the universe ages. Such ideas exist in theoretical physics, but they are not easy to fit to the data. A field that behaves almost exactly like a cosmological constant for most of cosmic history, then begins changing only in the last few billion years, needs an explanation for that timing. Why would it remain nearly still for so long, then shift when the universe is already old? That question is not a minor detail. It becomes the central difficulty. A model can be adjusted to match a curve, but a good physical explanation should show why the curve has that shape. The recent hints about evolving dark energy therefore create two problems at once. The first is, observational are the hints real? Or are they caused by hidden systematic effects in the surveys, the supernova data, or the way different measurements are combined. The second is theoretical if the hints are real. What kind of physics can produce them without damaging the many successes of the standard model? Both problems remain open. Webb's discoveries connect to this issue indirectly. Webb is not primarily a dark energy survey telescope, and its images of early galaxies do not by themselves measure the pressure of empty space. But they depend on the same cosmological framework that dark energy helps define: the distance to a galaxy, the age of the universe when its light was emitted, and the growth time available for early structures all rely on a model of expansion. If dark energy has changed over time, then the relationship between redshift, distance, and age may require adjustment. For most Webb galaxies, such adjustments may be small within current uncertainties. The importance is not that every early object would suddenly move to a different era. The importance is that the same framework already strained by the Hubble tension may also contain a second uncertainty in the behavior of dark energy. The expansion rate asks how fast space is stretching now. Dark energy asks why that stretching accelerates and whether the cause has been stable. Together, they form the background against which every early galaxy and black hole must be interpreted. The situation is made more delicate by the fact that the standard model remains highly successful. It is not a weak theory waiting to be replaced by any anomaly. It explains the cosmic microwave background with remarkable precision. It describes the large-scale clustering of galaxies. It accounts for the broad history of expansion and the relative amounts of ordinary matter, dark matter, and dark energy inferred from many observations. Any revision must preserve those successes. This is why cosmologists move carefully. A hint of changing dark energy is not enough to announce a new universe. It is enough to ask whether the simplest version of the old one is beginning to show stress. The same pattern has appeared throughout Webb's early science. The telescope did not erase the standard model. It made the early universe more specific, and specificity exposed pressure points. The massive galaxy candidates became less extreme after follow-up work. But a population of bright early galaxies remained. Early black holes may have several possible origins, but their timing remains difficult. Little red dots may combine starlight and black hole light in complicated ways, but their abundance and compactness still demand explanation. Dark energy follows a similar rhythm. The simplest interpretation may survive, but the data now invite more careful tests. The next stage will depend on larger surveys, better calibration, independent methods, and a patient comparison between instruments. If the hints fade, the cosmological constant will remain the preferred explanation, strengthened by another challenge survived. If the hints grow stronger, then the universe's acceleration will have to be understood not as a fixed property of empty space, but as a changing part of cosmic history. That would alter the deepest long-term question. The universe's fate is not decided by galaxies alone, because galaxies are small compared with the expansion that carries them apart. It is not decided by black holes, even though they can dominate their local environments. It is decided by the balance between gravity and whatever dark energy truly is. If dark energy is constant, the future tends toward endless dilution. If it weakens enough, gravity could eventually regain importance on the larger scales. If it strengthens, the acceleration could become more severe than the standard future allows. At present, the evidence does not choose one of these paths with final confidence. It gives a range of possibilities and a reason to keep measuring. That uncertainty is not a failure of science. It is the current shape of the evidence. The oldest galaxies tell astronomers that structure began early. The Hubble tension says that the expansion rate is not yet fully reconciled. The dark energy measurements now suggest that the force behind acceleration may also need closer examination. The universe that Webb helps reveal is therefore not only large in space and deep in time, it is still unsettled in its basic description. The final section must follow that uncertainty to its natural end, where different forms of dark energy lead not to one future, but to several possible endings. The future of the universe is not decided by the size of galaxies, but by the behavior of expansion itself. Galaxies can merge, stars can form and fade, black holes can grow, and clusters can gather matter into enormous systems. Yet all of these events happen inside a wider geometry that is still changing. Space is expanding, and for the last several billion years that expansion has been accelerating. The cause is called dark energy, because its nature remains unknown. Not because the effect is vague. Its influence is measured through distance, redshift, galaxy clustering, and the changing rate at which the universe is stretched over time. If dark energy is truly constant, then the future follows one path. If it weakens, another path becomes possible. If it strengthens, the ending changes again. The important point is that these are not stories invented outside science. They are different outcomes allowed by different physical behavior in the expansion. The first possible future is the one that has been favored for much of recent cosmology heat death, also called the Big Freeze. In this scenario, dark energy remains close to a cosmological constant, and the universe keeps expanding forever. Gravity still binds galaxies, stars, planets, and local groups where matter is already held together strongly enough. But across larger distances, the expansion wins. Distant galaxies drift beyond the region from which their future light can ever reach the Milky Way. Over immense spans of time, the observable universe becomes poorer in outside information. Star formation slows as gas is used up, heated or locked into long-lived remnants. The brightest stars die first. Smaller stars last far longer, burning gently until their fuel is gone. Eventually, new stars become rare because the raw material for making them is no longer gathered into cold, dense clouds often enough. The universe does not end in a single event under this picture. It thins, cools, and loses activity. Black holes remain for extraordinary periods, then slowly lose energy through quantum effects that are far too weak to matter on human or stellar timescales. The final state is not dramatic in the ordinary sense. It is a universe where usable differences in temperature and energy have faded, and where very little remains capable of changing. Heat death is not called that because everything becomes hot. It is called that because the organized flow of energy that makes physical processes possible has run down. This future fits naturally with dark energy that does not change in a way strong enough to reverse or intensify the expansion beyond its current trend. It is the calmest of the major endings, but it is also the loneliest. The second possible future depends on dark energy becoming stronger as the universe expands. This is the scenario known as the Big Rip. It requires a form sometimes described as phantom energy, where the pressure-driving acceleration becomes more extreme over time. If that behavior continued without limit, expansion would not merely separate distant galaxy clusters. It would eventually challenge structures held together by gravity, then by weaker and stronger forms of binding. At first, only the larger systems would notice. Clusters of galaxies would lose their shared gravitational connection. Later, galaxies themselves would no longer hold together. Stars would be pulled away from their systems. Planetary orbits would fail. Much later, if the strengthening continued all the way down to small scales, even ordinary matter would no longer remain intact. The Big Rip is not the leading settled expectation, because it depends on dark energy behaving in a very specific and extreme way. Current evidence does not require that ending. yet it cannot be dismissed purely by preference, because some measurements have left open the possibility that dark energy may have behaved differently in the past than a simple constant would allow. The challenge is to determine whether those hints are real, and whether they indicate a temporary behaviour or a long-term direction. A brief period of phantom-like behaviour in the past would not by itself mean the universe is headed for a rip. The future depends on the full evolution of the dark energy component, not on one limited interval. This is why better measurements matter so much. A small uncertainty in dark energy today becomes a large uncertainty when projected across cosmic time. The third possible future returns gravity to the centre of the story. If dark energy weakens enough, or if what looks like a positive energy of empty space is only a temporary state, expansion may not continue forever. It could slow, reach a maximum scale, and eventually reverse into contraction. This ending is often described as a big crunch. Although modern versions can differ from older forms of the idea, in a contracting universe, distant galaxies would no longer retreat beyond reach. Over time, the scale of the universe would shrink. Background radiation would grow hotter rather than cooler. Matter would become more crowded. Structures that expansion had separated would be drawn back into a denser state. The final collapse, if it occurred, would be a return to conditions where known physics becomes incomplete, because gravity, quantum effects, heat, and density would all reach extremes beyond ordinary description. Such a future is not favoured by the simplest constant dark energy model. It requires the acceleration to be temporary, or the underlying energy balance to change. Recent theoretical work has made this possibility worth discussing again, not as a prediction, but as a reminder that the sign and stability of dark energy are not minor details. If the apparent acceleration is a phase, then the universe may be in the middle of a long transition rather than on a permanent path. The difficulty is that no present measurement has followed dark energy long enough to decide its final behaviour directly. Cosmology infers the future from the past and present, and the present evidence still allows more than one ending. Webb's role in this final question is indirect but important. It was built to observe infrared light from distant galaxies, not to announce the fate of the universe. Yet by revealing unexpectedly bright early galaxies, rapid chemical enrichment, and early black hole growth, Webb has made the timeline of cosmic history feel less settled. It has shown that the first few 100 million years contained more activity than many models expected. At the same time, other measurements have kept the Hubble tension alive and raised questions about whether dark energy is perfectly constant. These issues are not all the same problem, and they should not be forced into one simple explanation, but they share a common effect. They reduce confidence in the idea that the broad outline is already complete. The universe can still be described by a strong standard model, but the edges of that model are active. The earliest galaxies press on formation theory. The expansion rate presses on measurement and possibly on physics. Dark energy presses on the final direction of time at cosmic scale. What Webb has revealed, then, is not merely overwhelming size. Size was already known. Its deeper contribution is evidence from a period that had been difficult to reach. Evidence detailed enough to make the old uncertainties sharper. A galaxy seen when the universe was only a few 100 million years old becomes more than a distant object. It becomes a test of how quickly stars formed, how soon heavy elements appeared, and how early black holes gained influence. A deep field becomes more than a crowded image. It becomes a record of structure forming across time. A spectrum becomes more than a line of data. It becomes a way of placing matter, light, and chemistry into a sequence. That sequence is still incomplete. The final ending of the universe remains tied to measurements that are still improving. Heat death remains possible if dark energy is stable enough. The Big Rip remains possible if acceleration strengthens without limit. Collapse remains possible if acceleration is temporary and gravity ultimately returns to dominance. None of these futures is close in any human sense, and none changes the immediate behavior of stars or galaxies around the Milky Way. Their importance lies in what they reveal about present ignorance. The universe is not only vast, it is also difficult to finish conceptually. Its beginning is observed through fading radiation and ancient galaxies. Its middle is measured through expansion, structure, and chemical history. Its ending is still inferred from a force whose nature is not known. Webb has not removed that uncertainty. It has made the uncertainty more exact. It has shown that better vision does not always make the universe simpler. Sometimes it reveals that the simple picture was only simple because the evidence had not yet arrived. In the end, Webb does not make the cosmos feel smaller by bringing it into sharper view. It makes the unknown more precise. The earliest galaxies are no longer only imagined from models. They have light, distance, chemistry, and structure. Some appear where the timeline is narrow. Some carry signs of stars that must have lived before them. Some may hide black holes that grew faster than simple pathways allow. Around them, the larger architecture of the universe continues to take shape through filaments, clusters, voids, and flows of matter that reach far beyond any single galaxy. Closer to home, even the Milky Way's position inside that structure may matter for the way expansion is measured. Farther out, the oldest light and nearby distance ladders still disagree over one of cosmology's most important numbers. Beyond both, dark energy remains unnamed in any deep physical sense, known by its effect and still uncertain in its future behavior. The story does not end with a final answer, because the evidence has not yet chosen one. Heat death, rupture, and collapse remain different possibilities tied to what empty space is truly doing. What remains steady is the method. Light travels, instruments improve, models are tested against what arrives. Some expectations survive, others narrow, bend, or fail. The universe does not become less wondrous when its mysteries are measured carefully. It becomes more real. Its scale is not only in distance, but in the patience required to understand it, one faint signal at a time. Webb has opened a deeper window into that patience, and beyond the window, the oldest light continues to arrive quietly, carrying the unfinished history of everything.